Can I have your attention? So, chaps, so can you put those laptops away, please? Especially those people looking at football at the back. Thank you very much. The guy with the red laptop, if you put that away, that'd be fantastic. Thank you. So, firstly, I'd like to say that I've got a lot of material to cover. So, sorry. I've got a lot of material to cover. I average about 80 slides. Guy with the fuzzy hair, thank you. I cover about 80 slides a lecture. Now, the reason for this is simple. I'm a professional electronic engineer, okay? This is my livelihood. I know about electronics. And I work in the mechanical engineering department. And my job is to teach you guys electronics. And you only get 10 credits of electronics. Worse than that, you only get 5 credits of me, okay? So you've got like 11 lectures of me. And then that's it for your whole career, okay? Now, unfortunately for you guys, the whole world is no longer a mechanical world. It's an electrical world, okay? So when you go into industry, everything's going to be run by computers, electricity. So these lectures are absolutely critical for you to understand and attend. I see we've only probably got about half turnout today. They're critical for your career. And if you miss this 10 credits, we're really bad at it. It's going to, by default, make you a really poor mechanical engineer, okay? So these lectures are like super important, so please encourage your friends to come along. And having said that, what I've tried to do in this lecture is effectively just give you what's really, really important and boil down the most important things of electrical engineering as I can. Okay. The other piece of information is that I'm trying to record these lectures so you can help you revise later. Now, I've not really done this before. I tried with MATLAB last semester. It sort of worked okay. So you see I've got a camera at the back, and I'm recording off my microphone. So my plan is to upload these somehow to the internet or something so that you can use it later. And I don't promise that this will work, because it's quite difficult to do. Because sometimes the camera might not work, sometimes the audio here gets lost by IS. So do come to the lectures, even though I'm recording. And you know, don't trust that the recording's going to happen. And I make no promises this will work. Okay? And if you come in super late and waltz around the front, you might be on the video. Right, so that being said, this is lecture 1, and I've called it Counting to 1024 on Your Fingers and Getting Robots to Pour Beer. So here's an overview of today's lecture. Firstly, I thought I'd tell you about me and why I should teach you about electrical engineering. Now I thought I'd tell you about what electronic and electrical engineering is and why you should care. And then I thought we'd look at representing information in digital circuits, shaft encoders, and then we'd look at some very, very basic logic, so OR gates, AND gates, and NOT gates. So, it's a bit difficult here. I love electronic engineering. I've been studying it, working in the field for about over 15 years, so 16 years now. And this is what I do every day. And I spent my PhD basically designing inter-satellite communication systems, telecommunication networks, and lasers for cancer surgery. So, I've got a very good background in this, so what I tell you is probably correct. Currently, I work on renewable energy, so this is a big problem facing all of our lives. We're running out of basically fossil fuels, oil, coal. And my particular research interest at the moment is looking at solar energy and trying to make more efficient and lower cost solar panels like these that go on your house's roof. And the big problem with solar panels, or these blue ones that you see on roofs as you go around the countryside, is you need a huge amount of energy to make them. So you have to turn this sand, this silica, into a working solar cell. And this takes a tremendous amount of energy. And basically, you get this energy by burning coal, okay? So when you look at this, you think, oh, that's nice, environmentally friendly. Don't think that. Think, oh, they burn lots of coal to make those. That's rubbish, okay? And in fact, after I've told you this, I'll move on to the actual lecture content. In fact, if you add up all the energy that the whole world has used to make solar cells from 1970 to about 2010, we've only just started to make that energy back by harvesting the sun's energy. So they've only just started to pay back in terms of energy because they're so inefficient to make, basically. So, very, very high energy things. There we go. There's a nasty power station. So I'm interested specifically in a special type of solar cell called a plastic solar cell. that has basically got very, very low energy components. So it's made of plastic, which is basically very, very cheap. And you make it by effectively depositing this mixture of sort of polymer and this sort of ball-shaped molecule onto this plastic substrate. And you can, because this thing's flexible, you can include it in sort of clothing very easily. You can put it on parking lot roofs very easily. So this is what I spend my life doing. And yeah, so now we're going to move on to what I'm going to teach you in this course. So I think electronic engineering is a really, really fantastic subject. And I think Arthur's tried to get this across to you. It's really a fantastic, exciting subject. And it really does make our modern world go round. So I'm going to try and sort of convince you of this as we go through this lecture course and try and make it as stimulating as possible for you. So it is really a vast and wonderful subject. And 10 credits gives it no, it's not worth 10 credits. It's worth like a whole degree. It is such a broad, wonderful subject. And it basically spans from quantum mechanics, so literally quantum mechanics that the physicists are interested in, into sort of electromagnetic waves, so telecommunications, to running your cruise missile to make sure it hits your target, okay? So it's an incredibly broad subject, and it's a very interesting subject. Now, I can't teach you everything, as I've said, but I will try and teach you the bare essentials so you can basically interface with electrical engineers. So there's a cruise missile and a microwave. So the focus will be practical. I'm going to teach you practical things. So I've basically deleted all the equations and theory that the electronic engineers will learn because it's sort of mathematics based. And I've tried to cut out sort of all the fluff and just focus on what we will need. So when I teach you something, it's going to be a directly useful thing. So I'm not going to teach you sort of theoretical things. And when I say don't bother learning this because the computer can do it faster, I mean that. So I'm going to really tell you what is important. Now, there is some theory, and when we get to things like operational amplifiers, it's quite maths heavy, but I cannot do anything about that. And I've done, what's there mathematically, you must know, okay? I can't cut out any more, okay? So it's really bare bones of what you need. So, what is electronics, and why do I need to learn it? So Arthur's been teaching about electrical engineering. So there's two words, there's electrical and there's electronic engineering. Arthur's been teaching about electrical engineering. And there's a ship motor. So this is actually an electric motor. That's a huge electric motor that's used to run a ship. And that's electrical engineering. This thing is allegedly a 50 kilowatt motor. And you can imagine it running on something like 500 volts, 100 amps. And that's certainly enough to kill you very easily. And you can think about electrical engineering as sort of big voltages, big currents that do useful work, okay? Like drive ships, drive cars, run lifts. Anything that involves doing actual work is electrical engineering. And it's clearly a useful thing for mechanical engineers to understand. Here's more examples of electrical engineering. So this massive dumper truck here is actually an electrical dumper truck. And it's electrical because, of course, we all know the torque of electrical motors is very, very high at 0 RPM. So you get maximum torque from an electrical motor at 0 RPM. And that's not the case with a diesel motor. So what they do, and obviously you can imagine this thing being full of rocks and on a slope, and you need all your torque to start off. So what they do is they use a diesel motor to run a generator. So you always keep your diesel motor running at the optimum condition. Then you use that to power the electrical motors that are attached to the wheels, which means this thing has got massive torque at 0 RPM. And you'll figure that out if you look at the induction motor torque speed curve. Another example of electrical engineering is this Tesla car. Who's heard of these Tesla cars? Who's heard of them? A few? Who hasn't? Okay. Well, it's basically an all-electric car, okay? So, unfortunately for you guys, the internal combustion engine will die, diesel will die, petrol will die. In maybe 50 years, nobody will be driving internal combustion cars. They're all going to be electric like this, which means it's even more important for you guys to understand about electrical engineering because you'll need that to get a job. And I think this is a fantastically fast car. It's something like 0 to 60. I think it's 2.9 seconds. I think it's actually faster than that. And it's run by a single electric motor. Okay? So this is all electrical engineering. This is big voltages and big currents. Electronic engineering is what I'm going to talk to you about. And this is basically small currents and small voltages. And generally, I like to distinguish it as sort of electrical engineering is currents and voltages that can kill you. And electronic engineering is voltage and currents that can't, okay? So that's how I like to think of it. So all general electronic devices run at like 5 volts, 50 milliamps, so not enough really to kill you unless you're really trying. So here we've got a massive jet engine, okay, the Rolls-Royce jet engine or something, and on the side of it we've got this bolted this box, and this box is the engine management system. And this makes sure that the engine's running optimally all the time. And in there, there'll be computers, there'll be processors, there'll be digitizers, there'll be all types of electronic devices, so smart electronic devices running at 5 volts, 50 amps. So you can think of sort of electrical engineering as the sort of the muscle, and electronic engineering as the brains, okay? So sort of electronic, this is what we're going to learn about. We're going to learn about effectively how to control your robots and your brains. If you could not sit near the camera, that'd be brilliant. Thank you. It's my camera, by the way, so if you knock it over, I'll be really upset. Another example of electronic engineering is this MakerBot. So clearly we've got some electrical engineering running the motors that sort of move the bits around. But then on top of it, you can see there's some small low-voltage circuitry that's effectively the electronic engineering. So this is the clever bit that's running it. Okay? So all the clever bits are electronic engineering, and they're all low voltage, low power. So here we are sort of again. We've got sort of effectively the brains, which is the circuit, all very, very low voltage, and then sort of the brawn, which is the motor, very, very high voltages. Now, I think we're going to look at a video. So I think this video is quite nice in distinguishing between electrical and electronic engineering. So this was a DAPRA challenge. So it's some US Defense Department robot, probably designed to kill people more efficiently or something. But anyway, it's quite cool, the robot itself. So just watch what the robot does. Oh, maybe I've got an audio lead too. Hang on. I don't have an audio lead. Hang on, maybe I can. I know what I'll do. So watch what it's doing. Watch how it's almost human-like actions. Climbing over bricks, climbing up ladders. So this is a pretty cool robot. I think it's meant for like rescue situations when you're trying to get people out of nasty environments. Go through doors. And the minute he does stuff I can't do, he's got amazing hands that rotate. Look, I think he's even playing with a key in the door. And he closes it behind him. Absolutely amazing robot. And when you can't open the door, just cut through it with a hand tool. It's pretty cool, right? Wow. And I can't do this with my hands. Well, I can do that. But not this. He's got a good trick with a fire hose too. I don't know what that stands for. Probably like Death Robot. And he's walking across like, it's a bit Terminator-like. It's a bit scary. Yeah. So that is a pretty cool robot. Now, if we look at that robot, we can sort of divide it up quite nicely into two parts. So we've got sort of effectively the legs and the arms that are your electrical engineering. So this is what Arthur's been teaching, this stuff that, moves stuff. And on the top of him, you can see there's this massive sort of control box that's full of electronics. And that's the actual, difficult part to make, the electronics that, drives it and tells him what to do and where to move his arms. So that's what this lecture is on. This lecture is basically on the top part of this robot. Okay. So knowing how to design smart electronics is essential for your 3rd and 4th year projects. And before we can design effectively complex robots, we need to know how to do some basic electronics. So that's what we're going to do in this lecture. We're going to basically lay the foundations of your electronic engineering. So the most important thing to do is to know how to store information, because that robot, as he's going through the environment, was aware of his environment and was storing information and was using sort of stored programs to interpret the environment around him. So one of the most fundamental things we need to do in electronic engineering is to be able to, let me just check my microphone, is to be able to store information. So this next section of the lecture, we're going to look at information storage. So, right. The easiest way to store information in an electric circuit is having a circuit on or off. So, we can actually do this with a lecture theatre. We're going to risk this. So, we can store information like this. So if I, for example, turn the lights on, these board lights on, that's storing information. This circuit is on, and we can define a circuit being on as storing information. We can say this is a 1. A circuit being on is a 1, okay? Now if we turn this circuit off, we can say a circuit being off is defined as a 0, okay? So we've got a way to store a 1 or a 0, or to count between a 1 or a 0 and store information in an electrical circuit. So here's off, this is 0, and here's on, this is 1. Now this is good, we can count to 1 now, so we can the robot can store a 1 or a 0, which is quite handy. But if you ever wondered when you looked at electrical equipment like your phone or your CD player or whatever like that, and you wondered why there's a 1 or a 0 on it, it's because there's this sort of international standard that says a circuit being on is a 1 and a circuit being off is a 0. So that's why all electronic gadgets like dishwashers have 1s or 0s on them. It's like I'm on or I'm off. So, how do we store more numbers? Can anybody guess? How do you store more numbers? Go on, somebody be brave and shout out. How do you store more numbers? Sort of jumping ahead. Yeah, I was you again. Somebody apart from you. How do you store more information? The answer's really easy. The guy with the beard. Yeah, go on. The guy with the beard and the white T-shirt. Yeah. Binaries. Yeah, okay, that's sort of the answer. Well, the actual answer I was looking for, you heard him. The actual answer I was looking for is just have more circuits, okay? So now what we can do is we can have multiple circuits that we can turn on or off, okay? So we could store a 1 and a 0 here, a 1 and a 0 here, a 1 and a 0 here, 1 and a 0 here, 1 and a 0 here. So now we've got the ability to sort of store multiple numbers in the circuit. Now what we do is if we label each one of these light bulbs with a number between 1 and 16. So the first one we give a number of 1, the second one we give a number of 2, the third one we give a number of 4, the fourth one we give a number of 8, and the fifth one we give a number of 16. And effectively, notice these numbers are doubling each time. So this is 1, 2, 4, 8, 16. So if we want to store the number 1, we turn on light bulb 1. If we want to store the number 16, we turn on light bulb 16. If we want to store the number 17, we turn on light bulb 1 plus 16, okay? And it goes on. Or, we want to store 21, we turn on light bulb 16, 4, and 1. Now, this is actually, in essence, how real computers store real information. This is all they do. They turn on, basically, lines of electronic circuits being 1 or 0. So this is how everything stores information. Now, very often, as engineers, you need to draw out these, they're called binary numbers, as that man said, in quite a handy form, okay? And sort of to do manipulation with them and to write them down, to give them to your coworker. And it's not very convenient to draw out circuits like this, because you've got to draw like 5 switches, 5 light bulbs, a battery. This is not an efficient way to write down these sort of electronic information. So let's get rid of the circuit for a start. Let's just get rid of the circuit. So now we've got rid of the circuit, and now we're sort of storing the same information. So we've got a light bulb on, off, on. Now, it's also still quite a lot of effort to draw light bulbs. So what engineers do is instead of drawing light bulbs being on or off, they just write down 1 or 0 to represent the information that's stored. So we've got 1, 0, 1, 0, 0, 1. And this is called a binary number, as 2 people have said. And it's called binary because you can think of bicycle. A bicycle has got 2 wheels, so 1 or 2. And the binary number has only got two types of number, 1 or 0. Okay, so it's a binary number. Ones represent on, zeros represent offs. So this is counting in binary from, and basically just by extending this number out over here, we can count as high as we want. So there's no limit to how high we can count in binary numbers. You can have 64-bit binary numbers where you can count sort of incredibly high, or even 8-bit binary numbers that count up to 256. So if we were to count in binary, we can actually count up in binary now. So we can go 0, 0, 0, 0, 0 is 0, 0, 0, 0, 0, 1 is 1, 0, 0, 0, 1, 0 is 2, 0, 0, 0, 1, 1 is 3, 0, 0, 1, 0, 0 is 4. Get the idea? Any questions? No? Right, well, it's your go now. So you can finish off this table. So you can fill out the numbers from 7 to 12. Okay? So off you go. And I'll wander around and see how you're doing. We don't have long for this, so just do it as quick as possible. It doesn't matter if you make mistakes. The most important thing is have a go. Okay? And I find the most important thing to do when doing this is to write columns. So write one column, next column, next column, next column, next column, and put numbers at the top, and just jot down ones in the right columns. Okay? So have a go. There we go. We've got 4 numbers already. Very good. Very good. Somebody's got 4 numbers. Just have a crack at it. Don't. Very good. Not so good. Texting. Can I risk this with my coffee? Oop. How are you doing over here? Somebody's left. How you doing? You done it? Very good, very good. Okay. So I think everybody's had a go at this. Most people have got I'll give you another few seconds to do it. Facebook, not so good. Okay. So I think everybody's had a go at that. So the most important thing about that is just have a go. And I think if you've got 3 or 4 numbers, then you've probably got the idea of what's going on. Okay. Anything not clear so far? Okay? Do shout if it's not clear, because I'll very happily repeat stuff, okay? So this is the correct answer. And this will be on Moodle, so you can look at it later. Oh, incidentally, I've not printed out lecture notes, because I thought it's a bit redundant. Do you want printed lecture notes? Show of hands, who wants them? Okay. Who doesn't want them and doesn't care? So you want them? Okay. I'll kill some trees then and print them out. Right. So each one of these ones or zeros is called a bit. Okay. So that's the technical word in a computer. So you might hear somebody talking about an 8-bit computer, or guys, I can't talk over you. So you might hear people talking about an 8-bit computer, or a 16-bit computer, or a 32-bit computer. And all this means is basically how many wires it uses to store information. So if we had a computer that could only store these 5 bits, that'd be a 5-bit computer. So what's the maximum number we can count to with 5 bits? The guy in the red shirt. What's the maximum number we can count to with only 5 bits? Yeah. So how'd you do it anyway? How'd you figure it out? You add those numbers together, wouldn't you? So 16 plus 8 plus 4 plus 2 plus 1 is, I think, 20-something. Okay? So if we had 8 bits, the maximum number we could count to would be 255. So it'd be 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 is 255. And in general, what we can say is that the general formula for figuring out how high you can count is 2 to the n minus 1, okay? So if you've got n bits, you can count to 2 to the n minus 1. So for example, here we'd be able to count to 31. Now, this is a mistake people quite often make. That's how high you can count, okay? So you can count to 31. But 0 is a number 2, right? So there's actually 32 combinations that you can count that you can, there's actually 32 numbers because 0 is also a number, okay? So this is important when you design things like sensors. We'll talk about that in a minute. So, shaft encoders. For this, no, I'm not going to have a volunteer this time because it'll take too long. But for this, we need some beer. Right, here's a glass. I'll do it here. I'll get rid of my coffee. Here's a glass. Here's some beer. And here's a bottle opener. Now, at the risk of absolutely destroying the lectern, what I'm going to do is, so I don't know if this is shaken up or not, I'm going to open this with my eyes closed, and I'm going to pour it into the glass with my eyes closed, okay? And you're all going to watch me get the keyboard wet, okay? So I'm going to open it with my eyes shut, plop. I know where the glass is, pour it into the glass, and tell me if it's going on the floor. Got my eyes shut. Okay, it's getting rather high. I've got no idea if it's going on the floor. Oops. So I've got beer all over the lectern. Right, so the point of that is, oh, I'm not going to drink that, by the way, because it's alcohol-free, firstly. It's a year old, so it's probably out of date, and it's warm, so there's no way I'm drinking that. Right, but the point is, how did I know, with my eyes shut, where my hand and the glass were? Yeah? How did I know that? My eyes were shut. I could still do the operation. And the way I knew this is because in my arm, there's nerves, okay? And the nerves tell me, or you, if it's you, where your arm is. So if you hold your arm out like this and shut your eyes, you know your arm is out. And if you move your arm like that, you know it's in this position because the nerves in your arm are telling your brain where your arm is. This is how you can do actions with your eyes shut, sort of. Whoops. The same thing is true for robots. So when you've got these robots in factories doing very, very precise operations, they need to know where they are repeatably. And you could use computer vision, but to be honest, it's not very accurate. Well, it's getting more accurate, but it's not really down to sort of millimeter precision. Giving robots eyes is a huge headache. So the easiest way to figure out where the robots are is to use some type of sensors and embed these sensors in the robot arm, and so the robot can figure out where it is. So this is the type of sensor that we use to figure out where the robot arm is, and it's called a shaft encoder. So what you do is you have this rotating shaft, okay? So you can imagine this shaft being attached to something that moves. So you can imagine, if my thumb's the shaft, you can imagine attaching it to a thing that's moving. Then as the arm moves, the shaft of this shaft encoder here will rotate. And what we do is we shine light through the holes in this disc. Light goes through the holes into a light detector, and then when we move, basically, what happens is the disc blocks the LED or lets light through, and the light detector will register a 1 or a 0, a 1 or a 0. So we've got some idea of how fast or how far our arm has moved. And you might attach this to a car wheel, for example, to figure out how far it's gone, or you can attach it to anything and figure out how far it's gone. But this is a very good method of doing that. So there we go. There's our shaft encoder. There's our magical robot arm, and it's moving its arm, and it's registering our signal. What's the problem with this? So anybody but you who's playing with his phone, what's the problem with this type of shaft encoder? What doesn't it tell you? Think about it. You want to shout out and be brave? No? Nobody? I was lecturing in electrical engineering yesterday, and they were very brave. They're all shouting out. Okay? Well, what this doesn't tell you is it doesn't tell you the position. It tells you it's moved, okay? Because if you looked at this signal, you could say, the arm was moving. It's moved. It's moved 1, 2, 3, 4, 5 notches, right? But it doesn't tell you its absolute position. So you'd still get the same signal. So if my arm was the robot arm, if you moved it from there to there, it would produce the same signal as moving it from here to here. There's no actual position encoding. It just tells you it's moved, which is quite a pain if you want a precise position of your robot arm. So before we move on, this is actually a real shaft encoder. So this is sort of industrial grade shaft encoder you might see in an actual robot arm. It looks a bit like a motor, but in there you've got the disc, and it's sort of in that packaging to protect it from grease and water and everything you might find in a factory. So this is how you'd actually buy them. So what we do to solve this problem of not knowing exactly where the arm is we have multiple little lights in our disc. So what we do is here's our disc, and here's our shaft again. And what we do is we have 3 LEDs. So there's one here, one here, one here, and 3 detectors, one here, one here, one here. And we cut a special pattern in our disc. Now, can anybody recognize this pattern on the disc? What's that pattern? Would recognize that? Where's the guy, you with the, who got the answer right last time? It's binary. See, the answer works twice. What this is this is binary. So look at it. It's black, 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 so that's 0, 0, 0. Black, black, white, so the light would go through here, so that's 0, 0, 1. Then we've got off, on, off, that's 2. Then we've got off, on, that's 3. We've got on, off, that's 4, etc., etc., okay? So it's binary code on the disk. So by cutting these holes into our disk, we can figure out exactly where it is, how far it's gone round. So here, this disk has got 1, 2, so we've got 3 numbers in our binary code here. So we can count up to a total of 7. So our disk has got 7 positions. So we know that if it's off, 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 it's between 0 and 45. If it's off, off, on, it's 45 to 90, all the way to on, which is 111, and it's between 315 to 316. So if we want more precision on this disk, all we need to do is increase the number of bits, and the precision of our device gets very, very accurate. So these things, they're very, very accurate. They're sort of, really millimeter precision. So you can have, multiple bits on this and really, really have a very, very accurate sensor. So here we go. So there's 3 bits in our sensor. So 1 plus 2 plus 4 is 7. But 0 is also position, so we've got 8 positions. So 360 degrees divided by 8 is 45 degrees accuracy. If we add another bit, we have 1 plus 2 plus 4 plus 8 is 15, but 0 is also a number, so we have 16 positions, so 360 divided by 16 is 22 degrees. So it goes on and on, okay? So, right, so I think I'll continue the beer theme with this video. So what I'd like to show you with this video is effectively, how accurate shaft encoders are. So this next video is all done with shaft encoders, and it really is millimeter precision. Okay, so just watch how accurate it is. One second. I just want to try and get this audio going. Ah, that's why. There's no audio, right. Oh, that sounds a bit too high. Right. It's not playing. 1 second. Okay, so well, go back, sorry. Excuse me. I'm a bit thrown because my audio is not working. Right, so here we go. So this is ABB is a German robot manufacturer, okay? They make lots of industrial robots, and they make huge, huge robots. And what that sign says in German is basically, please follow the instructions exactly, otherwise you'll break the robot and we won't get any beer for the evening. So there's some glasses. I don't know. There's the ABB robot interface. So we've got a beer there. Look how accurately it's grabbed that beer, how accurately it's moving it. And then what's going to happen is this other robot's going to open the lid of that beer. But look how accurately, that's really, really millimeter precision. So this is all done with these shaft encoders. And it opens it just by nudging it. And then watch this. It grabs this glass. Again, absolute millimeter precision. And then it moves them together, so it doesn't crash and break the glass. Absolutely in synchronization. So this is all done with these shaft encoders that will be in this joint of the robot. spilt a bit there. But, you know, that really is, you know, and if you could do that in a factory, you'd be very pleased most of the time. That's the most important bit. There we go. But you see, this is all being controlled really, really exactly. And even after that really rapid movement, it still knows where it is with the shaft encoders. Right, well, I think that's enough of that. But you get the point, is that you don't need fancy computer vision to do you know, these types of tasks. Yeah, very good. I think we've done enough advertising for them and that brewery. Okay, so we've got a few minutes left. What I'm going to do is I'm now going to look at logic gates. So I've got about 5-10 minutes left. Who's done logic gates before? A few of you. Okay, so this is going to be a refresher for those guys, and it's not going to be a refresher. It's going to be like new for some other people. So this is the first step in making circuits smart. So logic gates. So this thing here is going to be full of clever control circuitry, so full of sort of clever chips that make decisions. And we're going to look at some of the very fundamental elements of these chips. And it's so important to understand these individual elements correctly, because once you understand these, then you can very, very quickly, and we will actually, move on to building massive circuits that appear to be smart. They aren't, but they appear to be smart. So let's look at the AND gate. So whenever you get given an electronic component or a symbol, very often with it you'll have something called a truth table, even if it's a really complicated thing like a sort of Intel chip or something. And what this truth table is, it's literally, it tells you what the chip will do. So it gives you the inputs, so in this case it's A and B, and the outputs. And if you put A in, or if you put whatever you put on the input, it'll tell you what it'll give on the output. So this is an AND gate. An AND gate looks a bit like a square. So there's a square with a round end, and this is called an AND gate. And you might see, I think if you look in American textbooks, you might see a slightly different sign, or maybe old British textbooks. But anyway, this is the modern symbol for an AND gate. And it's got two inputs. It's got input A and input B, and it's got this output Q. So we can see that when we put 0 and 0 onto the AND gate, we get 0 out. When we put 0 and 1 onto the AND gate, we get 0 out. When we put 1 and 0 on the AND gate, we get 0 out. When we put 1 and 1 on the AND gate, we get 1 out. So the thing about the AND gate is you only get an output when both inputs are 1. So what A and B are 1, you get 1 on the output. So it's an AND circuit. Now this might seem really, really simple, but very, very quickly you can use these gates to build incredibly complex circuits and memory elements that we'll be doing later, even computers, actually. So here's an actual AND gate. It's not just some theoretical concept that I dreamt up to confuse you. This is actually an AND gate chip. And it looks like this. So you can see these pins here. This is where you put the signals in and out. So here it's got 1, 2, 3, 4, 5, 6, 7 pins. 1, 2, 3, 4, 5, 6, 7. And inside this chip, there'll be 4 AND gates. So there'll be an AND gate attached to this pin with inputs there and there, and an output there. And to make this work, you've got to give it a bit of voltage, so about 5 volts between this pin and this pin. I'll just tell you about these chips a bit now. So looking at this chip, we can tell this symbol here on the top is a Texas Instruments symbol. So these are the very famous chip manufacturers called Texas Instruments. We can tell, this is the date code here, so we can tell this was made in 1976 in the 45th week. So it's really a really old chip, this one. Actually, these chips were like state-of-the-art, I think, round about the time they went to the moon. But they're still used, and you can still buy these things, and they're made in millions. So that's an actual AND gate. So let's look at an example of using an AND gate. So imagine you've got a burglar alarm, and you want to ring the alarm when the burglar alarm is switched on and somebody steps on the pressure pad. So we've got two conditions. The alarm has been set, and someone steps on the pressure pad. Then we want the burglar alarm to ring. So what we could do is we could use an AND gate. So we have an input signal from our off-on switch, an input signal from our foot on our pressure pad, and the output going to our burglar alarm. So the circuit would look like this. So this is like the actual circuit. So you'd have a power supply, have two little switches, alarm set switch, pressure pad switch, and then the siren. So we've got input A and B and Q. That's it. Any questions on that? Any burning questions? Okay. OR gates. So an OR gate is just like an AND gate, except it's got this curved end here. It's got this like curved end. It's still got two inputs, A and B, and one output of Q. And Q will only go high, so it'll only go 1 to 1, when one or the other inputs are 1. So when we have 0 and 0, it'll be 0. But in all other cases, the OR gate will give you an output. So 0 and 1, 1, 1 and 0, 1, 1 and 1, 1. And so this will only go on when one or the other, or A or B, are high. Okay? So it's slightly different to the AND gate. Now you might use this, for example, in a fire detection system for an aeroplane. So imagine you've got an aircraft. There's a, don't know what that is actually. I think it's a B something, not sure. Anyway, it's got two engines, and you can imagine having a fire sensor in each of those engines, and you'd like the pilot to be alarmed that there's a fire in one of the engines when either of the engines has a fire. You don't want to wait till there's fire in both engines before you tell the pilot to do something. So an OR gate is what you need. So here we have fire in engine A, 1, sound alarm. Fire in engine B, no fire in engine B, sound alarm. No fire in engine A, sound alarm. Fire in engine B, sound alarm. So whenever one or the other of the inputs is 1, we get a 1 on the output. There we go. There's our little circuit. 2 inputs, 2 switches, siren. So the circuit will sound the siren when you've got a fire in one engine or the other. Any questions so far? Okay, so we've got 5 minutes. Final one is the NOT gate. So this is pretty simple. This is actually what it says. It gives a 1 when the input is 0, and it gives a 0 when the input is 1. So it's like the other way. So it'll invert the output effectively. So here we've got the truth table, and it's only got one input this time. So here's A. So 1, 1, output 0. Input 0, output is 1. So it basically flips the signal. So if you put 1 in, it'll give you a 0. If you put a 0 in, it'll give you a 1. And this little symbol here, this little circle, means not, basically. That always means not. And you can actually, I'm not going to go into this now, but you can actually attach this little symbol to any other gate, and it's like inverts the output. So here's an example in big. So when the input is off, the light bulb lights. When the input is 1, the light bulb doesn't light. So it's inverting the signal. So I think that is it for this lecture. So are there any questions? Right. So today's lecture was quite gentle. Whoa, hang on. So today's lecture was quite gentle. Please don't. Whoa. Thank you. Today's lecture was quite gentle. The next lectures we'll have to pick up the pace because we're going to sort of get deeper and deeper into this. Tomorrow at 9 o'clock, I think, or whatever the time is, there's going to be an examples class. Now, I don't know what Arthur has been doing. Guys, if you just... Thank you. I don't know what Arthur has been doing with you. In fact, I think he's been doing little seminars and things with you. So the way I propose to run the examples class tomorrow is I'm going to toughen up the examples sheet and put in some more difficult problems in the next hour or so. And then we'll probably go through the more difficult problems in the examples class. So rather than being a seminar, it's going to be like, I'm probably just going to run it in a structured form where you do question 1, I run through question 1, you do question 2, I run through question 2. I think that's how I'm going to run it. And I might also cover some more advanced topics in later example classes like Boolean algebra and things like that. So it's worth coming. And that's it. So thank you very much for your attention. And have a nice week. I think we see each other again on Tuesday.